Hello everyone. This work is led by Wei Wei from the HKUDS laboratory at the University of Hong Kong. The co-authors of this work include her supervisor, Professor Chao Huang, and Dr. Liang Haoxia. Next, I will be representing them, present an overview of this work to you. Online multi-behavior interaction platforms have become the prevailing tools for sharing and shopping today. For instance, when users shop on Amazon, they engage in various behaviors such as click, favorite, cart. Then they will proceed with the final target behavior for the platform, which is the buy behavior in online shopping platform. In general recommendation, a single type of behavior modeling is insufficient for comprehensively capturing the diverse user intents. The issue of data sparsity poses a challenging problem in recommendation systems due to the sparse nature of a single type of behavioral data. Besides, user behavior patterns are constantly evolving. Previous work cannot capture time-involving patterns of user-item interactions. For example, they cannot model dynamic users' preferences. Failure to address the aforementioned issues may lead to overfitting in the recommender system due to data sparsity issue. This will result in inadequate modeling capabilities and an inability to capture accurate user preferences. Additionally, since user preferences are dynamic and subject to change, failure to capture them properly can also impact the stability of the recommender system. Recognizing the aforementioned issues, the author believes the following approaches have the potential to mitigate them. First, introducing multi-behavior data into the framework to leverage auxiliary actions in modeling user preferences for the target behavior, thus elevating data sparsity issue. Second, making full use of time steps in the data to model dynamic user preferences. To this end, we propose a multi-behavior dynamic contrastive learning framework for recommendation. To achieve an effective multi-behavior, time-involving recommendation framework, there are two challenges that need to be addressed. First, model multiple behavior-specific semantics that are relevant to each type of user-item interaction dynamically. Second, capture the customized commonalities and diversities across different behaviors. In other words, the proposed solution must address complex and multiple relationships. Therefore, specifically, the author gave the following solutions. They have developed a multi-relational graph encoder that captures short-term preference heterogeneity while preserving the dedicated relation semantics for different types of user-item interactions. Moreover, they design a dynamic cross-relational memory network that enables the model to capture users' long-term multi-behavior preferences and the underlying evolving cross-type behavior dependencies over time. To obtain robust and informative user representations with both commonality and diversity across multi-behavior interactions, they introduce a multi-relational contrastive learning paradigm with heterogeneous short and long-term interest modeling. Next, we will dive into the specific details of these three modules. Regarding the short-term multi-behavior graph encoder, they partition the data based on time steps and specific user behaviors to obtain multiple time and behavior-specific graphs. Subsequently, they employ homogeneous graph neural networks and bipartite heterogeneous GANs to obtain item embeddings and user embeddings separately. Then, the learned behavior-specific metrics will be concatenated into a high-dimensional matrix to model the cross-behavior multiple relationships. Regarding the long-term dynamic cross-relational memory component, It is built upon the foundation of self-attention mechanism. Specifically, they treat the multi-behavior representations at the current time granularity as a query in self-attention, and the representations at the previous time granularity as a key and value in self-attention to model cross-temporal and cross-behavior relationships. The design modules enable each user to model cross-temporal and cross-behavior relationships. The specific matrix dimension transformations and the process are presented in the table on the right-hand side. The long-short-term multi-behavior contrastive task component encompasses the same contrastive learning task for both long-term and short-term behaviors. The approach involves merging the representations of multiple behaviors into a fused representation. Subsequently, each individual behavior representation and the fused representation are utilized as contrasting views for the contrastive learning task. This component aims to model the commonalities among multiple behaviors as well as the diversities between different instances within those behaviors. The specific objective function used for contrastive learning is InfoNCE. Instances with the same ID and different behaviors will be brought closer, while instances with different ID will be pushed further apart. This approach aims to capture the commonalities across modalities while amplifying the differences between different users to mitigate the over-smoothing issue. In the subsequent sections of the paper, the author provides theoretical foundations and justifications for this modeling approach. By employing the aforementioned methods, the authors obtain a recommender system that can model complex multiple relationships. It has the ability to capture patterns between user behaviors and model user preferences that evolve over time, thereby providing accurate recommendations and enhancing the user experience. The specific experiments were conducted using real-world recommendation system data. Comprehensive experiments have demonstrated the effectiveness of the proposed method. The author compared the GNN-based approach with a baseline method that considers sequential relationships. The experimental results demonstrate that the model outperforms the various baseline methods, achieving state-of-the-art performance. In addition, they conducted application studies to validate the contribution of each component in the model. By replacing the long-term dynamic cross-relational memory component with a GRU and removing the long short-term multi-behavior contrastive task, they evaluated the effectiveness of key module. Additionally, to assess the model's capability in handling sparse scenarios, they conducted group testing by dividing users based on their interaction counts. The results demonstrate that the model outperforms other baselines, particularly in sparse scenarios. In addition, the author conducted visualization experiments to intuitively observe the impact of key components in the model. The TSNE visualization experiment demonstrates that the effectiveness of contrastive learning in modeling the cross-behavior relationships across instances. In the original vector space, the differences between behaviors are more pronounced. However, in the vector space learned through contrastive learning, the differences between instances are more emphasized. The parameter experiment on the temperature coefficient in contrastive learning reveals that smaller values tend to yield better results. However, excessively small values can lead to gradient explosion, hindering the model's training stability. The visualization of self-attention across behaviors and time reveals that the number of behaviors has a significant impact on the performance. This work has been published on arXiv, and the paper includes the details of the proposed approach. The code implementation has also been made available for interested individuals to explore and utilize. Due to unforeseen circumstances, the authors are unable to attend the presentations in person. Today, I'm representing on their behalf, providing an overview of their work. For further details, please contact the authors via email to discuss any specific inquiries or requests. They welcome anyone interested in their work to reach out to them for further discussions or collaborations. Thank you all for your attention and participation. Thank you.
Thank you. And again, they're open to your email questions. You can also put questions